this lecture right here is all about it's all about moving on a little bit with centripetal acceleration and tying a link to it to the universal gravitational equation that we talked about. But starting off here, I like this example. What it deals with, it says if a stuntman rides a bike through a loop or a loop-the-loop, draw a free body diagram for the stuntman and the bike. Assume they are one object and at the top of the loop. All right, assume no friction. So what we're saying here is that this person maybe is riding a BMX bike or something, just pedaling around this circle till they get enough speed to ride upside down, and there's nothing holding the bike to the maybe the metal cage they're in or something along those lines, and they're just able to do this because of the velocity they're traveling and because of their inertia. So the question is, what is the minimum speed to be able to go upside down on a loop-the-loop like this? And so what we can start here is doing a free body diagram. So let's go ahead and draw a dot in the center of our object. Once again, the person and the bike are just one object. And we'll go ahead and draw the first force, which I think is obvious, which is force gravity. And then the second force, which is always perpendicular to the surface. And the surface is above the person, so the bike. And so force normal is going to point from above downward like this. All right, so this net force, which is obviously, or should be obvious that it's pointing down because we have Fg pointing down, Fn pointing down. This net force pointing down is going to give us a net acceleration pointing that way too. So I'm saying that, let's see, F net is pointing into the center, and therefore A net is also pointing into the center. And this net force and this net acceleration, instead of causing the person and the bike to fall, is causing the person and the bike to turn in a circle. All right. Let's go down here. If the rider travels the minimum speed, what is the force normal equal to at the top of the loop? All right. So obviously this person can go faster and faster, and he'll make the loop easier, right? It'll be easier for the person to make the turn if they're going fast. But we want to know what the very minimum speed is. And at the very minimum speed, the wheels of the bike just lose contact with the track. And if that's the case, let's write that down. So if the rider travels the minimum speed, what is the force normal equal to? We can say the wheels lose contact, or we can say just barely lose contact. And Fn, if there's no surface, then is equal to 0. All right, 0 newtons. So it then says derive an expression for V min to travel the loop-loop. Call into the center positive x. Okay. So what I want to point out here is when I get a problem like this, a lot of times down is negative. Whenever I get a circular motion problem, I like to call into the center the positive x direction. It just makes things easier. And because if an object is traveling in a circle, then it's going to have a centripetal force pointed into the center, a net force into the center, an acceleration net into the center, and therefore it's going to be positive, and it just makes our life easier. And because sometimes, both of these forces aren't going to point into the center. In fact, they're going to fight sometimes. So if the person was on the bottom of the track, or the bottom of the loop. Okay, so in this case, then let's sum our forces in the x direction. I think I have room down here. Set it equal to max. So our positive x forces, obviously force gravity and force normal. We have the mass of the bike plus the person. It's just one mass. And then their acceleration into the center is going to be a sub c. Because we said that the net force is, right, this is F net, and the net force is going to be Fc. So that's where force centripetal shows up. And therefore Fc is the same as m times a sub c, right? And okay, so a sub c, though, we know is v squared over r. Fg is mg. Move over a little bit there. Fn, we know Fn, right? And I shouldn't even have wrote it. What is it? Well, we said the wheels just barely lose contact with the track, and Fn is 0. So therefore, we can actually get rid of this plus sign here and just cross off Fn here, right? Because it's going to be 0. And so we just have mg then is equal. I mean, if you really want to write the 0 in there, you can, plus 0. Mg is equal to m times v squared over r, right? So something like that. And you should notice now, something that's pretty amazing to actually see, is that it doesn't matter how much the bike's mass or the rider's mass is, right? It could be a little kid. It could be a 200-pound person. It could be, it could be a large bike or a small bike, or a Hot Wheel. It doesn't matter, because the mass is going to cancel away. That this velocity to go around the loop and go upside down is independent of the mass of the object. All right, let's multiply both sides here by r and get that off the bottom. So we end up with v squared over here is equal to rg. And then we can just do the square root there, right? Because we have v squared equals rg. So then we can write it this way. V equals the square root of gr or rg, whatever you want to say. And this is going to be the minimum speed to travel the loop. Now, obviously, you can go faster than this, and it would be much safer, right? Because if a person is going around this loop and they don't travel the minimum speed, they go too slow, then they would come off of the path in a parabola, right? They would come off, they would have to at least go a little further, and then they would fall in a parabola, right? And so we see something like this happening, and or something, where they, yeah, I mean, you get the idea, right? I mean, it wouldn't be great if you were traveling slower than the minimum speed. So anyways, the next question says, well, what if the person had a mass of 100 kilograms and the loop has a radius of 3 meters? I think the M got cut off. 3 meters is about what, 10 feet or so, right? So that seems realistic for a giant metal caged in area for a BMX bike. Let's go ahead and calculate that. So I think I have room here. So we're saying then that V min is equal to the square root of 9.81 times 3. And notice that the fact that the person had 100 kilogram mass didn't matter, right? we said it was independent of mass. So if we multiply 3 times 9.81, I think it's like 29.14 or something. But I'm going to type it in my calculator anyways, just to double check. 29.43. All right, so let's go ahead and square root that. Get about 5.42. Which, you know, what is that? That's in meters per second. What is that in miles per hour? Double it and then add some. So maybe 14 miles an hour or so. 12 miles an hour. So decently fast to get around that track, that loop. Then it says, what is true of the wheels when traveling the minimum speed? And I just wrote this on here because I was afraid that maybe I would forget to say it in lecture. The wheels just lose contact. Or I think sometimes kids would sit through the lecture and they would get that force normal is 0, but they wouldn't really think about, oh, well, why was that, right? What was true of the wheels at that point if your normal force is equal to 0? Okay. If the rider stays in the loop and travels in a circle multiple times, and draw a free body diagram when the rider is at the bottom of the loop. So when the rider's at the bottom of the loop, and this is what I tried to mention before, if we draw our dot here, now force gravity obviously is still pointing down and still the same. But what's going to have to happen here is the normal force is going to have to be larger than force gravity. So it cannot be 0. And the reason for this is that you want, when you're at the bottom, and you're in circular motion, right? You need F net to point into the center, and therefore A net is into the center. And this will cause you to turn into the circle. So what I'm saying is when you go through say you're driving in your car and you go through a valley, you can think of this valley as being part of a circle and giving you circular motion, right? So having a net acceleration, so a segment, an arc segment, right, of a circle or an arc segment, a valley can be a segment of a circle and have those properties. You don't have to have an entire circle there. So that green segment could just be the piece of the circle to make this true, that the force normal is larger than Fg, and therefore the F net or A net is into the center. But this has to be true if the object is in circular motion. I think sometimes when I ask that, kids always think they're equal there, and they're not because of the loop-the-loop. All right, how does Fg compare to Fn at the bottom of the loop? So we can say here Fg is less than Fn. Why? Fn, or we can say, focus on Fg because that's kind of what the question says. Fg must be less than Fn so that F net is directed towards the center. So the F net has a magnitude that is directed towards the center. Oops. Struggling to write today. I'm going to write and is equal to Fc. Or I'll actually write it out. Force centripetal. So Fg must be less than Fn so that Fnet has a magnitude that is directed towards the center of the circle and is equal to force centripetal. All right. So that is why. So force gravity can't become smaller, and that's important to realize. Force gravity is mg. So what has to change is force normal. So when the person is in circular motion, force normal changes to meet the situation or the requirement that F net it has a value, a magnitude, and points in towards the center. All right. If the stuntman has a mass of 100 kilograms plus the bike and the radius of the loop is 3 meters, and the stuntman decides the minimum speed to travel around the loop just to be safe when the normal force is equal to half of the force of gravity. All right, calculate the minimum speed. So, so what we're saying is we're talking about at the top of the loop, and talking about a situation like this. Can I draw this person on a bike? Probably not very well. All right, I don't know. It's something. Let's just move on. And we have a force gravity pointed down, of course. And then we have a normal force pointed down that that we are specifying is half of force gravity. So I could have been a little more careful there and drawn this force normal exactly half of this larger force gravity. Maybe that's closer right there. So something like that. Okay, so then over here, we'll sum our forces. We'll call into the center positive x, right? And so we can say F net in the x direction is equal to max. And we have Fg plus Fn is equal to m times a sub c, just like last time. We can say Fg is mg, and we can say that Fn is 1/2 mg, right? And that's what the problem stipulates. And we have m times v squared over r. Now, once again, because there's a factor of m in each of the terms, we can go ahead and cancel that away. So we end up with g plus half g is equal to v squared over r. So this is 1g. 1g plus half g is 1.5g, or 3 over 2g. I'm just going to write 1.5g is equal to v squared over r. Multiply both sides by r. And we are going to get v, whoops, I was going to keep that in black. V is equal to the square root of 1.5 gr. All right, and there you have it. So what is the actual answer, though? Maybe with numbers. The radius of the loop is 3 meters. Mass of the person is 100 kilograms, but that doesn't matter because obviously mass is independent of mass. So anyways, so now we have that 29.43 again times 1.5. So we're saying this time we have the square root of 44.145 meters squared per second squared is the units in there. And all right, so we end up with v equal to that. So we square root it, and we get 6.64 meters per second. So if we double that, then add some, definitely closer to 15 or 16 miles per hour as composed to, or compared to, I don't know what it was last time. Was it 11 or 12 miles an hour? Let's see, 6.64 meters per second for the VMIN, compared to what it was last time, which was 5.42. So it went up by what, 1 meter per second, roughly, a little over one. Yeah, a little over a meter per second, 1.2 meters per second. Okay. Good. Let's go ahead and go to the next part. So something I hinted at in another lecture, and I just want to work it out one more time here. And I think we actually did it in class, but I want to draw this comparison again so I know we have it. We have two formulas for forced gravity. We have one that is when you're on the planet Earth, right? Where you have your mass times the g of the planet you're on, right? And on Earth, this is 9.81. So something like that. And we also have this one, which is the universal one, between any two objects, g m1, m2 over r squared, where r is the distance center to center, m1 is the mass of object 1, m2 is the mass of object 2. What variable is the gravitational field on Earth? So I already said this before. I've said it multiple times, is that baby g, right? Baby g is the gravitational field. All right, and this is 9.81 meters per second squared. I think you can see that, but if not, there you go. Since Fg equals Fg, derive an expression for the gravitational field on any planet. So this gets at the idea, right, that kind of what I hinted at up here is that if you were on a different planet, then it would no longer be 9.81. You would have a g of a planet. So what I'm saying here is you can set these two forced gravity formulas equal to each other, and you get something like this. I kind of like saying that this is the mass of U. And here we'll say g times the mass of U times the mass of the planet. Because maybe you're not on Earth, maybe you're on a different planet, right? And you want to know what this G planet is. And divided by r, which is just the distance from the center of U to the center of the planet. So this is the radius of the planet. And you can see that the gravitational field of a planet does not depend on your mass. Meaning, like, there's going to be a field around this planet that causes objects to accelerate towards it, regardless of whether or not you're there, to experience that field or that acceleration. And so your mass mathematically cancels away. And we're left with this expression right here, the g of any planet, right? Because maybe it's the moon or maybe it's Mars or something, is equal to big G times the mass of that planet. Oh, did I forget to square my r? I think I did. Geez, typical. All right. So times the mass of the planet over the radius of the planet squared. Okay. And so this is how you would figure out, say, the baby G on the moon or the baby G on Mars. You would just plug in these values and solve. All right. So then a good way to check this, and we're just about done here, is just to plug in to see if this really is true for planet Earth. Is the G of Earth, right? Let me write that as Earth. Is that really 9.81? And so you can check it, right? You could plug in here, and this is what I believe we did in class. So if you didn't get this right in class, you should definitely try and plug this into your calculator again. We have the mass of Earth here and the radius of Earth. So the mass of Earth is 5.98 times 10 to the 24th. But this kind of gets at like how we know what the mass of Earth is, right? That if we can calculate the gravitational field on Earth experimentally, right? If we knew that that was 9.81 and we knew the radius of the Earth, we can calculate the mass of the Earth using this equation. And so that kind of answers some of these questions, right? Like, how do they know how massive the Earth is, right? Like, how can they know that? They didn't put it on a scale. 6.37 times 10 to the 6. So equations like this allow us to understand that's true, that this number is correct. All right, so here you have it right here. Don't forget to square your bottom. And I think if you do this, you can solve for 9.81. If I was doing this, and you should pause it here and give this a try, plug it in your calculator. But if I was doing it, the first thing I would do is I would multiply the top across, get a number, and then square the bottom and get a number. So if we do that, 6.67 times 10 to the negative 11th, make sure you're using your EE button. The EE button allows you to do the exponent on your calculator, times 10 to the. So I'd multiply that, use some parentheses, times 5.98 times, or EE, times 10 to the 24th, end parenthesis. So on top here, I'm getting about 3.98866 times 10 to the 14th. And I'm going to hold off on rounding till the very end, right? Because that's kind of the idea. Otherwise, you're just adding error throughout the problem. So you like to wait to round if you can. 6.37. Let's see here. I think I'm going to use some parentheses. 6.37 EE 6, end parenthesis, and then raise it to the second power. And on bottom here, we're getting like 4.05769 times 10 to the 13th. All right, so you can see there's a factor of 10 difference, right? Can you see that 13? Let me write that again. So there's a factor of 10 difference, which is baby g is about 10. So that makes sense. That this is gonna be correct. So let's go ahead and type this in. 3.98866 EE 10 to the 14th. Okay, and then we're going to divide that by our 4.05769 EE 13 end parenthesis. All right, so on my calculator, I'm getting about 9.8297. All right, so and it goes on. It's so an irrational number, it looks like, or maybe it stops right there. It's hard to say. So about 9.83. And which is pretty dang close to what we'd expect, right? So obviously there was a little bit of rounding here with the mass of the Earth and the radius of the Earth. But you can see that it checks out that this is very close to being 9.81. All right, so there's our equation for the baby g of any planet. And yeah, that's how we get that expression. All right, have a good day.